Here we're going to look at 10.1e and F. First in 10.1e, we're going to perform a significance test to compare two proportions. So let's go ahead and look at this example. Are teenagers going deaf? In a study of 3,000 randomly selected teenagers in 1988 to 1994, 15% showed some hearing loss. In a similar study with 1,800 teenagers in 2005 to 2006, 19.5 showed some hearing loss. Does this give convincing evidence that the proportion of all teens with hearing loss has actually increased? So they want to know if it's increased, so we're going to state our hypothesis. Clearly we have sample 1 and sample 2. Sample 1 is our first bit here, and then sample 2 I'm going to circle in the purple. They want to know if it's increased. So in this case it does make sense to do our difference of sample 2 minus sample 1. So let me first state my proportions. I'm going to have P sub 1 for my case be the 2005 to 2006 kids, and the P2 be the proportion of the 1988 to 1994 kids. Therefore, I can state my hypothesis accordingly. H sub O would be P1 minus P2 equals 0, because that's our null hypothesis. But what do we really think is the case? We believe it's increased, so we think that difference is going to be greater than 0. And that's the hypothesis we would state. So overall what you saw is here's what we formally just did on stating our hypothesis. It says here, if we want to determine whether there's a significant difference between two population proportions, we would take a random sample from each and conduct a significance test. The procedure for this test is essentially the same thing as it was for the one proportion Z test, with only the slight difference. It's in the null hypothesis itself. And we already stated this. In our null hypothesis, we said there will be no difference between the two proportions. That is, we did P1 minus P2 would be equal to 0. Now, when we established our alternative hypothesis, we had to determine what direction we wanted. Was it less than, greater than, or no difference? And on our previous example, we said greater than. So that's how you would establish your hypothesis. Now, before we talk about the complete test procedure, we do need to mention what's called the pooled sample proportion. This is a component that's actually used in the two-sample Z test of the difference of proportions. And it's labeled as P hat sub C. And what it means, it is a combined proportion. They want us to do this. Take the count of successes in both of our samples combined at the top, and then the count of the individuals in both samples combined at the bottom. So you're going to compute what's called the pooled proportion, which is going to be our successes on the top over both of our sample size combined. And let me show you why we need that. The actual two-sample Z test for the difference of two proportions, again, this is actually the name of it, is we've addressed the hypothesis already. The hypothesis clearly is going to be for the null that the difference is 0. Our alternative, we're going to decide if it's greater than, less than, or equal to. Now, the test statistic that is used to help us compute our p-value or our probability of our test statistic happening given H sub O is true is still going to be the same thing that you see in the formula sheet. It's the statistic minus the parameter over the standard deviation. So right here, our statistic is our p hat 1 minus p hat 2. It's what the data said. Now our parameter, we think the true difference is 0, so it's always going to be 0 here. However, major difference in between anything for proportions. This is very unique, and it's just for the test procedures for the difference of two proportions. The standard deviation of the statistic, you actually use the combined proportion for both of these. You do not use p hat 1 and p hat 2 like we did in the confidence interval. So make note of that. This tends to be a very common multiple choice question. Well, they will ask you what is the correct statistic, and if it's for a test, you need to look for the combined proportion, and again, not the individual 1 and 2. So more formally, here are the actual alternative hypotheses that you could conduct. You could say the difference is greater than, less than, or you could have a two-sided test where it's not equal to. Now, in terms of the conditions, what conditions do you check? They are the exact same conditions that you checked for the difference of two proportions for the confidence interval. Nothing different. You're going to show that there's a random sample of size n from population 1 and a random sample of size n from population 2. Or at least there was a randomized experiment, something that gives us randomness. To check for normalcy, we're just going to go on in and show again that at least there's 10 successes and failures in each of the samples. We're going to do n times p for sample 1 and n times 1 minus p for sample 1, and then do that for sample 2. We're then going to wrap up with checking our independence. So the sample of groups are independent, or the 10% condition of sampling without replacement. So just like we did before, we have to show both for sample 1 and for sample 2 that the 10% condition is met if we are sampling without replacement. Or we're going to look, did they state that they were taken independently, so we don't have to check the 10% condition at all. Let's go back to the hearing loss question and do it from start to finish. We already defined the state portion for that, so I'm just going to reveal what we had as our actual hypothesis. We're going to add this time though to that our significance, let's choose 5% for our alpha, and again we're going to define our proportions. For the planned portion, I'm going to state the particular test or confidence interval. So in this case, we are doing a 2-sample z-test for the difference in P1 minus P2. And I don't actually have to put the words here. I can do the symbols and I'll get full credit. Let's check our conditions. For randomness, the data come from random samples, that is stated. For normalcy, let's double check that all 4 of these conditions for sample 1, for the 2, and for sample 2 are greater than or equal to 10. All of the probabilities of successes and then those of failures are greater than or equal to 10, so approximately normal condition has been met. And then we're going to wrap it up with the independence. They didn't talk about independence in the actual example here, so we must show that they are independent because we are not sampling with replacement. So independent samples were taken, and there were more than at least 18,000 teenagers for that latter year, and at least more than 30,000 for the earlier year. Now for the do, I'm going to show you both what I would write down by hand and how to use the calculator for this one. Now you do need to show the pooled proportion for this because it's very specific to the test. So the pooled proportion, and the calculator will give this to you by the way, but if you don't do it with a calc, here it is by hand. I had what was the success for both cases? Well, for the 2000 year, 450 students had the hearing loss, and for the other one, 351. Where did that come from exactly? Well, here's what it was. Now, they never talked about the 450 students, but they told us 15% of 3,000, which is this, and then we have 19.5% of 1,800, which is this, and then our total counts. So the pooled proportion in this case is 0.167. Now, if you write out the actual test statistic, which we're going to use to find our probability, the z-score in this is actually going to be p hat 1 minus p hat 2 minus our hypothesized difference, which is 0. Then notice the pooled proportion. This is the exact same for both of the 2 samples. The only difference for the standard deviation is you put the corresponding sample size for each of the 2 samples. Now, based on this, the z-score is 4.05. If I were to find that p-value, the 4.05 is pretty high z-score. And remember, we think it should be higher. So what we would do is we could do a normal CDF. And we would just do our lower bound of 4.05 and our upper bound. Because this is a test statistic or standardized data, the mean is 0 and 1. Therefore, based on that, the p-value is going to be approximately 0, is what we get. Now, ultimately, I would just do this one on my calculator, so let me show you how to do the calculator keystrokes. It's very easy. When you come in, hit the Stat button, and we're going to go to the tests. Remember, we're looking for a 2 proportion, and it's a z-test. It happens to be number 6. If you select on that, you're going to be asked to show the successes for your first sample in the sample size, and successes for sample 2 in its sample size. Choose the appropriate test. Here we're doing greater than. You could actually click on draw, and if you did draw, you would get this approximately normal curve. And it's hard to see because the test statistic is right there. That's actually the area they're finding for us. Now, what would I copy over to your paper is I would write down the test statistic right here, 4.0479, which we saw right here that we got. This right here is the p-value. Be incredibly careful with this p-value. It is not 2.58. This is actually scientific notation, so you have to move that decimal place. Remember, if it's -5, would be 5 to the left. If you do that, you're going to get approximately 0.00002 and then your remaining digits. Basically, you're going to get a p-value of 0. Lastly, you're going to have p-hat1 and p-hat2, which we have accordingly here. And then make sure to write this one down here. This is your pooled proportion, which we computed at 0.167. So do write that value down. Again, the AP board is going to just remind you one more time, hey, if you type anything wrong into this calculator and you get these test values and when you put it on your paper they're wrong, you're not going to get full credit. They recommend coming back and actually showing the statistic in terms of those. It would be called a parallel solution. If this is different from the calculator, they're going to take the worst of the two, which means it doesn't matter even if you had the right answer on your paper. I recommend just do the calculator. If we have time, let's come back at the end of the exam and actually write this information down and double check your work. So just use your time wisely. First, I'm going to say, since p is less than 0.05, and let's write that down, we had 0 is less than 0.05. Since that's the case, we are going to reject H sub O, and we're going to conclude H sub A in context. So just read what H sub A says and just put it into words. Here's what we're going to say. We have convincing evidence that the proportion of all teens with hearing loss has increased from 1998 and 1994 to 2005 to 2006. This is just one way to make the conclusion. Again, I just recommend to folks when you struggle with it, take a look at what we had. We had said that P1 minus P2 is greater than 0. Literally just put words to the symbols. So you could say the proportion of, say, this year minus the proportion of this year was actually greater than 0, and you'll be completely fine. A little curveball to that study. Letter B. Between the two studies, Apple introduced the iPod. If the results of the test are statistically significant, can we blame iPods for the increased hearing loss in teenagers? This is a great review of Chapter 4, so you have to always keep this in mind if you want to make any type of blaming conditions or cause and effect conditions. Remember, since we do not have an experiment, we randomly assign some teens to listen to iPods and others to avoid listening to iPods. We cannot conclude iPods are the cause. You must have random assignment of some type of experiment case to be able to have a cause and effect situations. Basically, an experiment has to be into place. One thing we could say, though, is this. It is possible teens who listen to iPods also like to listen to music in their cars and perhaps car stereos that are causing the hear loss. So there could be definitely other factors out there that could be causing the hearing loss. So if we did do an experiment, Chapter 4, we better try to control for those other elements. Great AP mistake, they're just reiterating. Folks, be careful. When you fail to reject the null hypothesis, slow down. Never ever believe the null hypothesis is true. So don't ever go back and make that conclusion. I say it because they are going to try to trick you on the AP exam with this type of situation. In 10.1F, we're going to interpret the results of inference procedures in a random experiment. So let's wrap up with just this one example, cholesterol and heart attacks. High levels of cholesterol in the blood are associated with high risks of heart attacks. Will using a drug to lower blood cholesterol reduce heart attacks? The Helsinki Heart Study looked at this question. Middle-aged men were assigned to a random one of two treatments. We had 2,051 took a certain drug to reduce their cholesterol, and then a group of 2,030 took a placebo. During the first 5 years, 56 of those on the drug group and 84 on the placebo had a heart attack. Is there a benefit to middle-aged men who take this drug, and is it statistically significant? So we want to write a hypothesis, and we really could do it one of two ways. We want to define P1 and we want to define P2. So let me actually do that first. I'm going to go backwards on this. I'm going to have P1 be the actual heart attack rate for the middle-aged men that were on the drug, and P2 be the heart attack rate for those who were on the placebo. And we ultimately want to know, is there a benefit to this drug? So what could make sense? Well, either case, one thing that we do know is this. That we want to see if the drug is actually lowering it. So if the drug gives us lower heart attacks or fewer ones and the placebo is higher, if we do P1 minus P2, we think it's going to be a negative answer. So two ways you could state it. You could either write your hypothesis written in this format right here. We could say that the null hypothesis is P1 minus P2 is 0, but we really think the P1, that is the drug users, minus the placebo users, we are going to see a lowering of the heart attack, so this would be smaller, so it's going to be less than 0. Now, equivalently, what we could do is just a little bit of algebra. I could also move this P2 to the other side of the equation. If you do that, the hypothesis would just look like this, which is P1 equals P2, which we don't think that's the case. We really think P1 is less than P2 because our proportions of heart attacks will go down on the drug versus the placebo. Okay, let's go ahead and do the plan portion. Check the conditions. I'm going to first talk about the tests we're going to perform. We're going to do a 2-sample z-test for P1 minus P2. For normalcy, the data came from 2 groups in a random experiment. So in an experiment, it was randomly assigned, so we're covered. Now, for the normalcy part, we need to show that the number of successes of heart attacks and failures in the 2 groups, when we do that calculation, we're going to get these 4 different values. Where did one of them come from? For example, this first 56, I took 56 men out of 2051, so right here, times the 2051, and we got 56. So these are the corresponding values. And they're all at least 10 so that we know that the normal condition is met. Now for independence, due to the random assignment, these groups of men can be viewed as independent. The experiment itself is the random assignment, so independence is covered. You do not actually show the 10% condition in this, even though, yeah, we're sampling without replacement, but it's an experiment. So keep this in mind. This is one of the first times we've seen it. In an experiment, you don't have to show the 10% condition for independence. You wouldn't. The experiment itself is set up accordingly. Even though in this experiment, we're not replacing the people who are doing the experiment. Only in a study would you have to check the 10% condition if they are not doing replacement within the study. Now in this one, I am going to show the p-hat1 and p-hat2. P-hat1 and p-hat2 are for both either our drug or our placebo. And then we can do our combined proportion in this case. So our successes are 56 and 84 over the entire of both samples. So our pooled proportion is right there. If I were to write out the statistic for this, the test statistic as a formula is this formula. And if we just put in the corresponding values, we will get our test statistic. And it's going to look something like this right here. Now, what I want to do, this is a one-sided test. So if I look at the curve of what this would be, we're going to actually see that we need to find this test statistic value in anything less. So I need to find that area. To do that area, because I've already standardized the data, all I'm going to do is just do a normal CDF from negative 100 or negative 999 to negative 2.47, and it's been standardized as a z-score, so just use 0 and 1, and we're going to get a p-value of 0.0068. We can go ahead and make our conclusion now. Since the p-value is 0.0068 is less than our alpha in this case, I'm actually going to choose to use 0.01 just to kind of mix it up. Again, we normally use a 5%, but let's use that. With that value, p is less than 0.01, so we reject H sub O, and we can conclude there is convincing evidence of a lower heart attack rate for middle-aged men who take this particular drug than those who take only a placebo.